Okay, I get it. I got a question. Okay, let's see. So in the case of the problem with the top, so, okay, Rex, maybe you can turn on your microphone and ask the question.
So with the problem with the top, is the torque that was shown with the vector, is that created by gravity? And it's
yes,
it's pressure or it affecting the top? Okay. I was wondering if that torque was like the friction of the top on the surface, or what exactly that was caused by.
Yeah. So it can be on a frictionless surface, and it was the force of gravity.
Okay.
So for instance, a top far out in space, a spinning top far out in space, where no gravity is there, will not precess.
Okay. Okay, thank you.
Yep, no worries. Okay, so now let's quickly finish the rest of the slides. Okay, I will we are going to see a spectacular example of, in astrophysics, a spectacular example of L being constant. So just like the ice skater problem. So and we'll see an example where angular momentum is I times omega. I decreases for a star quite a bit as it dies, and so it'll spin much faster, just like an ice skater. Okay, when she brings her arms and legs in, her moment of inertia decreases and her angular velocity increases. Okay, so I'll go very quickly go over the evolution of a star. And again, this is just fun stuff. So, all right, so at the center of a star, the way they produce energy is they combine 4 protons, nuclei of hydrogen atoms, into a helium. Okay, so it's a multi-step process. I won't go through the details. So the effect is, the net result is you take 4 protons and combine them to helium. Now in the process, 2 protons are being converted to neutrons and so on. Now the deal is the following. The mass of 4 protons is 6.69 times 10 to the 27 kgs. The mass of the helium is that, 6.64. You can see the mass of the helium is less than the mass of the 4 protons. Okay. And that's what it takes to make energy. Anytime you take a bunch of ingredients and get a product, if the product weighs less than the ingredient, the missing mass is converted to energy. So let's say you take wood and burn wood, the product is ashes, ashes, water vapor, and carbon dioxide, and the products weigh less, and that's why you get energy. Okay. Anyway, so this is how stars produce energy. Okay. You take protons, combine them to helium, and the product weighs less, and then the missing mass is converted to energy by this equation, Einstein's equation. This is the missing mass. Okay, so the numbers are as follows. About 1 part in 140, so about 1% of the mass goes missing, and that's converted to energy. Okay, so at the center of the star, so let's, and again, this graph shows you iron is the most tightly bound nucleus. You can take any of these lighter nuclei and fuse them till you reach iron, and you will keep getting energy. And that's what happened in the center, and at the center of stars. If a star is massive enough, at the core, it's just fusing various elements till it gets to iron. And once it gets to iron, it cannot produce any more energy, and the fusion reaction will stop with spectacular consequences. In a nuclear reactor, we take heavy nuclei, split them, and you split them into smaller nuclei, and they're more tightly bound, and energy is released. Anyway, so this is a very good graph. This is a multi-million-dollar graph, but that's a story for another day. Okay. So remember that for a fusion reaction, you keep getting energy till you reach iron. Once you reach iron, you cannot get any more energy via fusion. So, so here are massive stars. So at the center of the sun, and again, if at the center of the sun, if you have temperatures above 10 million degree Kelvin, well, about 10 million degree Kelvin, hydrogen fuses to helium. If you want to fuse helium to carbon, you need a temperature of 100 million degree Kelvin, and if you want to fuse carbon, you need temperatures of 600 million degree Kelvin. Okay. Anyway, once iron is reached, no more fusion and energy is released to maintain internal temperature. So let's see what all this means. Okay, so here's a here's a star. Now we'll ignore the colors right now. So this is during the regular lifetime. So why is the stuff not falling down? Okay, so there's fusion reaction going on, heat is produced, and this pressure prevents this stuff from falling down. Okay, so that's the dynamic equilibrium of a star. Okay, so you need to produce heat, which will provide you pressure to keep all this stuff from falling down. So what happens once you run out of fuel and you can't fuse anymore? So that's what we were saying. So most stars are, when they start off, they're mostly hydrogen, they fuse to helium, and then helium fuses to carbon and so on. But once you reach iron, you can't fuse anymore, you can't produce any more energy, and you can't provide the pressure to prevent this collapse. Okay, and so let's go back one slide. Okay, so that's what so once iron is reached, no more fusion energy is released to maintain its internal temperature to apply outward pressure to hold up the star. The core collapses in a span of a second. So the core of the star, which is mostly iron, will collapse, and the outer layers fall in and bounce off the collapsed core. This gravitational energy is used to produce heavier elements than iron. So here's the star. The core, which is no longer producing fusion reaction, has collapsed, and now this stuff starts collapsing. The outer stuff starts collapsing. It comes and hits a hard surface, and it bounces back, and it collides with this stuff that's falling. Okay, so all this stuff gets compressed. All this fuel gets compressed to a high temperature. It fuses instantly, and this explodes like crazy. All this happens in a flash. Okay, and that's what we're saying. So the core collapses in a span of a second. The outer layers fall in and bounce off the collapsed core. The gravitational energy is used to produce heavier elements than irons. The bounce off the collapsed core produces a catastrophic explosion. That's the supernova. Okay. Now, if the core of a supernova has a remaining mass greater than 1 point solar mass, it becomes a neutron star. In a neutron star, the protons and electrons have been combined. Anyway, it becomes a neutron star. Okay. So when a star dies, if the mass of the core is less than 1.4 times the solar mass, this is the symbol for the solar mass, this becomes a white dwarf. Okay. If the mass is between 3 solar masses and 1.4 solar mass, then the core becomes a neutron star. Okay. And if the mass is greater than 3 times the solar mass of the core, then this becomes a black hole. Okay. So so when a star dies, it can become one of 3 things: a white dwarf, a neutron star, or a black hole, okay, depending on what is the mass of the remnant object. Less than 1.4 solar mass, white dwarf. But in this range, a neutron star, and greater than 3 solar masses, it becomes a black hole. Okay. So that is what this computer simulation shows. Okay, so this is 0 milliseconds. So at the center, you've reached iron, and it's and the iron core is collapsed, and then this starts bouncing off the iron core. This starts collapsing and bounces off the iron core, and then you have a supernova explosion. Okay. So red is the highest density, and yellow is the least density. So a star roughly between 2 and 3 times the solar mass, the size of the sun, eventually can collapse into a neutron star as it runs on fuel. Okay, so now here's what happens. The radius of the star decreases from about 1 million kilometers to a few kilometers. So imagine that ice skater, except that an ice skater can reduce her moment of inertia maybe just a little bit by a few percent. But when a star dies, when a star collapses, the radius of the star can decrease from 1 million kilometers to a few kilometers. So it can decrease its moment of inertia by a factor of, let's say, 100,000. And during its collapse, I decreases and the angular speed increases. A collapsed star can rotate as much as 1,000 revolutions a second. Okay. So imagine an object that is twice as massive as the sun, rotating at 1,000 revolutions per second. Okay, so that's a spectacular thing. And by the way, our sun rotates at 1 revolution per minute. Our sun will become a white dwarf. It won't become a neutron star. Okay, so let's quickly. Now it turns out that angular momentum, well, it's a fundamental quantity. Every particle, so every electron, for instance, is spinning, and it turns out, and every proton is spinning, every neutron has a spin. So angular momentum is a fundamental quantity, and it turns out that every electron, the angular momentum of every electron is, well, the spin quantum number is 1/2 h bar. Okay. So it has a spin of 1/2 h bar. So every electron is spinning at the same rate. Okay. So actually, the angular momentum, the value would be 1/2 plus 1/2 plus 1 by h bar. But anyway, we always say it has a spin of 1/2. Okay. Every proton has a spin of 1/2, and so on. So it's a fundamental quantity, and it's quantized. Okay. All right. And okay. All right. I can't seem to be able to get to my last slide. Oops. Oh, there you go. All right. So angular momenta are measured for particles are measured in this unit, h bar, which is Planck's constant divided by 2 pi. So there's the unit. And so this is the fundamental unit of angular momentum. And fundamental particles, okay, so have half integer spins. So there are 2 kinds of particles. Particles that have half integer spins or integer spins. These are called fermions, and those are called bosons, particles with an integer spin. So all these guys have integer spins. These are bosons. And this is what matter is made of. All the matter that we can see is made up of these guys. This is the up quark and down quark. each have a half spin. This is the neutrino, this is the electron. Protons and neutrons are made of up and down quarks and electron. So all these guys are heavier. These are heavier quarks and heavier leptons. Okay, they all decay. So anything made out of these will decay. Okay. Only stuff made out of these is stable. Okay, so every one of these guys have a spin of half. These guys have integer spins. Okay, so so the electron has 1/2 times h bar spin. This guy, the photon, has 1 times the h bar spin, and so on. Okay. And there's a theorem that states if you're a fermion, so if you're an electron, no two electrons can be in the same quantum state, and that's what gives the structure, the atom a structure, its electronic structure. Okay. All right, and so here's another example of angular momentum. In an atom, the electrons can only orbit in states where the orbital angular momentum is an integer number times h bar. So the first allowed orbital is 1 times h bar. That's where the quantum number n comes from. N equal to 2, here's the next orbital allowed orbital, n equal to 3. So the only allowed orbitals are where L, the orbital angular momentum is n h bar. Okay. So again, so angular momentum shows up everywhere. It's a very important quantity. All right, that finishes this chapter. So what I'm going to do is I'm going to open the floor for